Hello, everybody.
Jim, we don't have anybody in yet. Has
Okay.
the window been opened to let people?
Sorry, you just got it.
Okay.
Okay,
Let's wait a little bit.
I'll wait. Hello, everybody. Welcome to this week's Green Bank Observatory Community Zoom. I'm Jim Jackson. Just a couple announcements before we get on to our talk today. The Green Bank proposals are out. They were issued last week. And so you can find the details on the website. One detail you might want to look at is the ultra wideband receiver will not be widely available next semester. We're still doing some tests on it and some improvements. Will be scheduled intermittently, but it will be available, but just not, but only in campaign mode. There was a nice event at the National Science Foundation last week to announce the NANOGrav detection of a gravity wave background. Fabulous result using Green Bank data, among other telescopes. The NANOGrav team is to be congratulated for a really great scientific result. The data look compelling, and looking forward to collecting even more data to characterize this gravity wave background. We had a little issue with an old ephemeris. Apparently, we had an ephemeris that lasted from JPL that went extended into the future 20 years, and that was 20 years ago. And the ephemeris just ran out of its entries. But the software didn't catch it. So there was a couple of weeks where we had some data that had the wrong ephemeris information in it. And that means that the velocity scale, frequency scale may be slightly incorrect. We will fix that. We found a method to fix it. We're going to test it. The data should all be fixed on our side, and the users will be informed. We're expecting that process to take about 2 weeks. So stay tuned for that. And with that, I will pass it off to Jay Lockman, who will introduce today's speaker.
Let me pass it off to Ryan Lynch, who is the host today. And just to remind everyone, this is being recorded and will be available on our website in a few days.
And let me introduce our speaker, Dr. Nihan. So Jim mentioned the NANOGrav results that were announced last week. Nihan is a postdoc in NANOGrav at Vanderbilt University. He is also the paper lead for the NANOGrav 15-year anisotropy paper. And today he's going to give us an overview of these exciting new NANOGrav results. As usual, if you have any questions, please put them in the chat or the Q&A, and we will have time at the end for those. So I will now turn it over to Nihan. Take it away.
Thanks, Ryan, and thanks for having me over to give this talk. All right, so I'm assuming you can see my screen, you can hear me all right, and if not, just please shout at me. But hi everyone, I'm Nihan, and today I'll be giving this talk about the NANOGrav 15-year dataset and the evidence for a gravitational wave background that we found in this dataset. And before I begin, I just want to point out that I'm giving this talk on behalf of the whole NANOGrav collaboration. So all the work that I'm presenting here has been the culmination of efforts put in by a large number of people over the course of more than a decade. So these are by no means just results that are mine, but these represent the collective work of a large group of people. So really quickly, what are pulsar timing arrays or PTAs? So PTAs are a gravitational wave detector, which are constructed through timing many millisecond pulsars that are distributed throughout the galaxy. So we particularly want millisecond pulsars because they are very stable rotators, so you can essentially treat them as clocks in the sky. which essentially means that you can predict exactly when the next pulse or the next tick from your clock should arrive at the radio telescopes of the Earth. Now, when a gravitational wave passes between us, it stretches and squeezes space-time, so the pulse arrives either earlier or later than when we know it should arrive at the radio telescope. And using this, we can then infer the presence of a gravitational wave. So you can use a single pulsar to try and search for these gravitational waves, but given how noisy the interstellar medium is, you would need a really, really loud gravitational wave background to detect it using just a single Earth pulsar baseline. So what we do is we collect lots of these millisecond pulsars in our detector, and rather than just looking at each individual Earth pulsar baseline, we look at multiple baselines, and what we're looking for is, in particular, this cross-correlation signature, which is unique to an astrophysical background and takes the form of this Hellings and Downs curve as shown in this animation on the right-hand side. So this is sort of the unique signature of an astrophysical gravitational wave background that sets it apart from other sources that could be representative of noise in our dataset. So this brings us to NANOGrav and the NANOGrav 15-year dataset. So NANOGrav is an acronym for the North American Nanohertz Observatory for Gravitational Waves, and we are a collaboration based largely in North America, though we have collaborators around the world. And we are made up of more than 40 institutions, more than 90 collaboration paper authors at this point, and more than 100 members. And we are always looking for new collaborators. So if you want to get involved in nanohertz gravitational wave astronomy, feel free to reach out to me or any of your local NANOGrav members. We'll be more than happy to have you on in our collaboration. So with NANOGrav, we collect our data using the Green Bank telescope in West Virginia, the Arecibo telescope in Puerto Rico, and the Very Large Array in New Mexico. And for the 15-year dataset in particular, most of the data comes from the Green Bank telescope and the Arecibo radio telescope. But we now also have data coming from the Very Large Array, and that will grow in prominence, especially given the fact that Arecibo is no longer operational as of a few years ago. In addition to that, we will also have the CHIME radio telescope up in Canada joining our array of telescopes, and that will feature in our upcoming datasets as well. But for the 15-year dataset, this dataset contains 68 pulsars, and this is approximately a 45% increase from the 12.5-year dataset. And this is, I think, the single biggest jump in the number of pulsars that we've ever had in a pulsar timing array dataset. And in addition, for the pulsars that were already in the 12.5-year dataset, we've added in at least 3 more years of timing data to these pulsars. And so as a result of all of this, some of the highlights of this work include the development of a completely new timing pipeline based around POINT, which is a new pulsar timing software developed by people in NANOGrav. And we also have new and improved constraints on the astrometric parameters for the pulsars in the PTA, as well as new and improved constraints on the binary orbital parameters, including the masses of the pulsars and their companions for a few of the systems.
Hey, Nihan, could I just ask you to minimize the video gallery bar? Thank you.
Okay, hopefully that's out of the way. All right, so given that we have this fantastic new data set, let's go ahead and look at how we do our search for a gravitational wave background. So before looking at the results themselves, here's a quick overview of how we construct the likelihood that goes into all of our searches. So there's 3 main components: the timing model, the white noise, and the red noise. And so white noise represents noise that has a flat spectrum, whereas red noise represents noise that has excess power at lower frequencies. And by frequencies, anytime I talk about frequencies, I'm referring to gravitational wave frequencies for the rest of the stuff, unless I explicitly state that it's radio frequencies. So as you might expect, the timing model is largely defined through the efforts of the timing working group, and I showed some of the highlights in the previous slide. And so we have a timing model for each of the pulsar in the PTA. So while we are deriving the timing model, we also fit for the intrinsic pulsar red noise and white noise. And so this is an iterative process to converge on the timing solution or the timing model, coupled with the white noise parameters, which includes things like telescope noise or radio frequency dependent jitter noise, and then also intrinsic red noise that might be present in each of the individual pulsars in the PDA. And then finally, that leaves us with searching for the gravitational wave background, which manifests as a red signal or a red spectrum signal that is common to all the pulsars in the array. So when we're searching for the signal, we are fitting for the presence of the signal in all the pulsars in the PDA. And here's what we find. So on the left-hand side here, I'm showing the spectrum of this common red spectrum. And the gray violins on this plot represent the posterior probability density, where the width of each of these violins gives the probability of finding the excess timing delay shown on the y-axis. So what we see is that across all pulsars in our PDA, we see this excess power at lower frequencies, and the nature of this spectrum seems to follow that of a power law, which is shown by the black dashed line showing a power law with a spectral index of 13/3, and the blue dashed line which shows the best fit power law to this data. And the spectral index of 13/3 is important because that's the fiducial value that we expect for a gravitational wave background produced by a population of circular inspiraling supermassive black hole binaries who are driven purely by their gravitational wave emission. So as I said, you can go ahead and fit the spectrum with a power law template, and the plot on the right-hand side shows the constraints on the spectral index on the x-axis and the amplitude on the y-axis and the marginal posteriors on the panels at the top and the right. So what we find is that we recover a median spectral index of 3.2, but we still are consistent with that spectral index of 13/3 between 2 and 3 sigma credible regions. So, and this is slightly dependent on how we choose to model the noise in our PDA. But as I said at the top, we are not really looking just for the presence of this common process across all of these pulsars, because we already saw that in the 12.5-year dataset. What we really want to see is the presence of these cross correlations between the different Earth pulsar baselines in our PDA. And so what evidence that we have for the presence of this correlation, which was not present at a significant level in our previous 12.5-year dataset. So in this dataset, on the other hand, we also searched for the presence of these correlations, and I'm showing the Bayesian reconstruction here on the left-hand side, where we searched for these correlations using spline knots with the positions given by the violins on the plot on the left-hand side. And in addition to that, we also quantified the evidence for the presence of these correlations by using a Bayes factor, where the two models that we looked at were a Hellings and Downs correlated common spectrum process, and compared that against a common spectrum process that did not have any correlations. And so what we find is that we prefer the Hellings and Downs correlated process by a Bayes factor of about 220. And this can change depending on how you exactly model your gravitational wave background. And it can go as high as 965. But overall, the Bayes factor of 200 corresponds to about a significance at the level of, at a p-value of 10 to the minus 3, which is at the level of a 3 sigma detection. Similarly, we also, rather than looking at both the autocorrelation and cross-correlation information, we can also base our evidence for the background looking just at the cross-correlations. So we sort of ignore the information from the autocorrelations in the pulsar timing array. And so if we choose to go down that method, the correlations that we recover are shown on the plot on the left-hand side, along with the theoretical Hellings and Downs curve. And the associated detection statistic is shown in the plot on the right-hand side. And so this detection statistics corresponds to a significance at a level of, at a p-value level of 5 times 10 to the minus 5 to about 2 times 10 to the minus 4. So about a 3.5 to 4 sigma level detection. So what we see in this data set overall is that we, for the first time, are seeing positive evidence for the presence of these interpulsar correlations in between the pulsars in our dataset. And we've never seen this before in any of our pulsar timing array datasets. So really, for the first time, we are seeing the emergence of this nanohertz gravitational wave background. So you might say, that's great, but do we know what the source of the gravitational wave background is? Unfortunately, we don't really have a solid answer as to what it could be, though a lot of us expect that this background is probably produced by a population of inspiring supermassive black hole binaries. So on the left-hand side, what I'm showing is the posterior derived from the NANOGrav 15-year dataset in those green contours. And in the blue contours, I'm showing the expected gravitational wave signal that you would expect from these supermassive black hole binaries if these were all circular binaries and were being driven just by gravitational wave emission in their evolution. And so what we see is that, one, the background that we see in this data set is louder than what we would expect, and it is shallower than what we would expect. So what we seem to find in this data set is that if this background is indeed coming from a population of supermassive black hole binaries, then they would either need to be more massive or more abundant in order to explain the higher amplitude. And in order to explain the shallower spectrum, we might need to take into account environmental effects, which lead to a flattening or a turnover in the spectrum of the gravitational wave background at lower frequencies. And that's shown in the plot on the top right, where we can see that for the purple line, it is the predicted spectrum coming only from GW evolution of the supermassive black hole binary systems. Whereas if you include environmental effects, you begin to see this turnover at low frequencies. However, in this data set, we don't really have conclusive evidence yet for the presence of this turnover, so we cannot really see for sure one way or the other if we see this turnover in this data set. So if not supermassive black hole binaries, then what else could be the source of this background? So we also explored a bunch of different models coming from new physics. So things like inflationary gravitational waves, cosmic strings, superstrings, domain walls, or cosmological phase transitions. And so in this plot on this slide, I'm showing the base factor for the presence of this new physics process relative to a background that's predicted just from supermassive black hole binaries. And so what we see is that the base factors are really, at this stage, they are not anything significant to write home about. And so we really need more data in order to say for sure whether this background is coming either from supermassive black hole binaries or if it's coming from one of these new physics models that would be very exciting. So just to summarize everything that I've talked about, here with this data set, we report evidence for the presence of a nanohertz gravitational wave background in our pulsar timing array data set. And we have an inconclusive evidence to determine if the source of the background is supermassive black hole binaries or alternative newer physics models. I do want to point out that other PTA collaborations, so the European plus Indian pulsar timing array and the Australian pulsar timing array, as well as the Chinese pulsar timing array, have also published their results, and they also report varying levels of evidence for the presence of the background. So it's not just NANOGrav operating on itself. We have this large international collaboration, all of us working together in pursuit of this gravitational wave background. And finally, I want to end by saying that a combination of all of the PTA datasets through the International Pulsar Timing Array, which is currently underway, will yield the most sensitive PTA dataset that we've constructed to date. And that should help us answer some of these outstanding questions, particularly about the source of the gravitational wave background. And I'm happy to take questions. I have absolutely not done justice to any of these words, so I've tried to summarize more than 5 papers in this talk. If you want to go and read any of those in more detail, you can go to the website that I have in the title of the slide, and there you'll find links to all of these papers. And if you want to get in touch with me, my email is at the bottom. I'm happy to take questions.
All right, Nihan, thank you very much for a great talk on really interesting work. We already have a couple of questions in the Q&A, and if people have any others, please go ahead and put them in, but we'll start off with this one. How long will it take to confirm these gravity wave results? And I guess you could probably answer that in a couple different ways, so I'll let you take your pick.
Right, so if we are holding out for something at a significance level of 5 sigma, then it could come early as in the next couple of years in this next iteration of the IPTA dataset. But it might even come in the next NANOGrav dataset. We already have at least, 3 more years of data already collected. So it just becomes a matter of putting it together and analyzing it. So I would say 2 to 3 years.
And then kind of a related question, how far in the future could the source of the gravity waves be pinpointed to one system?
So that is more difficult to pinpoint because it really depends on what the underlying model for your emission process is. So it really depends on where this turnover exactly happens and when PTAs actually are able to probe those frequencies with any amount of sufficient sensitivity to actually see that turnover. So it's really driven by the astrophysical model that you choose to probe. So it becomes difficult to pin down an exact timing baseline. But again, we had a recent paper out about this with NANOGrav dataset, and we showed that if there's like a significant difference in the spectral indices for two different processes, for instance, then we could say something about the presence of an additional process by about the 20-year baseline. So about 4 or more years of data on top of what we already have.
All right, thank you. We have some more questions coming in. The next one is the gravity wave noise spectrum emitted at the instant of inflation potentially detectable? And I assume that means specifically with pulsar timing arrays.
It is predicted to exist in the PTA spectrum. We do not have evidence in favor of that model. So inflationary gravitational waves are the first model listed on this plot. And they are very mildly preferred over the supermassive black hole binary interpretation. So yes, it's predicted for this band, but right now we don't have evidence, and it really depends on how strong that signal is and how strong it is relative to the supermassive black hole binary signal, if you assume that both of those might exist in this band. But if you're interested, I would recommend reading up on the new physics paper that we have, which goes into a lot more detail about this.
Next question is, what unique role can low-frequency gravitational waves like these play in multi-messenger astronomy?
Yeah, that's an excellent question. So one of the key things in sort of defining the source of the background is, especially for the supermassive black hole case, is the detection of a single supermassive black hole binary. And so while in this data set, we do not have evidence for any single source, these sources are going to stay around for millions of years. So the sources that are in NANOGrav's band are not merging cataclysmic sources like the ones that LIGO or LISA might see, but they're going to be around, but they're essentially persistent sources of gravitation waves. So once we see these sources either using gravitational waves, then we can go on and follow those up with electromagnetic surveys using optical telescopes. And that will give us a way to perform multi-messenger analysis on these supermassive black hole binaries. So that's something that's particularly exciting, and that's one of the next things that PTAs are going to target, which is the detection of a single supermassive black hole binary.
And that was all the questions we had for right now.
I've got a question.
Yes, please go ahead, Jay.
Yeah. Sorry, I can't seem to submit it through the Q&A, but would you comment on the consequences of the loss of Arecibo to the sensitivity of the NANOGrav measurements?
Yes. So right off the top, I don't think I'm the best person to talk about this. So I'll try to summarize the opinions I've heard of other people. But obviously, the loss of Arecibo is huge. And we're trying to make up for that by adding in the very large array and the supermassive, and not supermassive black holes, but the CHIME radio telescope. And we've also moved a lot of our pulsars onto the Green Bank telescope. So something that we are planning to do in the future as well is propose for this DSA 2000 telescope, which is predicted to have the approximate collecting area of Arecibo. So that will also help us plug the gap that's left by the loss of Arecibo. So for the moment, we are mitigating the loss of Arecibo by moving a lot of our observing to the Green Bank, and then also folding in the Very Large Array and the CHIME radio telescopes. Yeah, that's what I have off the top of my head, but I can direct you to other people if you want to talk about this in more details.
Jay, maybe I'll just comment that both GBT and Arecibo contributed about equally to NANOGrav's sensitivity in the overlapping portions of those data sets. Arecibo because of its just raw collecting area and sensitivity, and the GBT because of its good, they're not quite as good sensitivity, but really what the GBT then provided was more angular baselines to map out the Hellings and Downs curve over wider angles. So that's kind of like the instantaneous hit, but luckily all of those years of Arecibo data will continue to contribute going forward. They provide like really essential long-term legacy data set. So losing Arecibo doesn't mean that Arecibo data no longer contribute going forward. All right, we had another question come in. This question actually has to do with something that Jim mentioned about the solar system ephemeris issue. And I will just say that if whoever put that in could maybe just reach out directly to Jim or someone else here at Green Bank about that, then that would be great. All right, do we have any other questions at this time? All right, if not, then I will thank Nihan again for a great talk, encourage people to look at those NANOGrav papers that have been published, and there will be more, I'm sure, in the works, and a lot of interpretation going forward. So thank you again, Nihan, for joining us, and thank you everyone else. And please join us again for our next community Zoom in 2 weeks.
Thanks all.